Hi everyone, this is a quick video showing that the t-distribution converges to a standard normal distribution. And this is a really well-known fact that we learned pretty early on in our probability courses or inference courses that I don't think I've seen the proof before. And I came across it and I thought it was really cool, and so I wanted to do a video. Now to do this proof, we're going to need to call upon the weak law of large numbers and Slutsky's theorem. So I went ahead and wrote out these properties before we got started. Now, the other thing we're going to need to know is how the t-distribution is constructed. And a t-distribution is the ratio of a standard normal random variable divided by the sum of squares of a standard normal random variables. So this is supposed to be I divided by n. Another way to think about that is y over a chi-square random variable. I'll leave the square divided by its degrees of freedom. So in this case, y is a standard normal. Zi is IID, standard normal for all I. And if we recall, the sum of standard normal random variables of n standard normal random variables squared is a chi-squared distribution with degrees of freedom n, which I'm denoting as chi. Now, we have that if we think of each zi as its own special random variable, we know that an individual zi squared is itself a chi-square random variable with 1 degrees of freedom. So zi squared, and the expected value of zi squared is actually equal to 1. The reason why we know this is because the variance of zi is equal to the expected value of zi squared minus the expected value of zi squared. Now, the mean of standard zi ends up being 0, which means the variance of zi is equal to the expected value of zi squared. And zi is standard normal random variable, which means it is equal to 1. We also know that it is a chi-square distribution, which is a very well-known fact. Chi-square distributions have finite variance. So we can use the weak law of large numbers here, thinking of each zi squared is the random variable, which are IID with a finite expected value and a finite variance, because chi-square distributions have a finite variance. Then we know that the mean of zi squares, so the sum I equals 1 to n, zi squared, which is our random variable, divided by n, is going to converge in probability to 1, because again, zi squared is considered the random variable, not just zi. And we know that, again, weak law of large numbers. Take a minute to think about it if that went a little fast for you. Now here comes Slutsky's theorem. In Slutsky's theorem, I use x's and y's. It's probably hindsight, maybe that wasn't the best call. But our chi-square random variable is the y in this case, and we have the denominator, which is the sum of zi's squared over n, or the square root of the sum of zi squares over n, converges in probability to 1. Now let's look at the top. Well, it's very clear that y is a standard normal random variable, so y converges to a standard normal random variable. So y converges in distribution to y because it is equal in distribution, which is a standard normal 0, 1. And the sum of zi squares divided by n, their degrees of freedom, converges in probability 1, which means using Slutsky's theorem, we have that t converges to y over 1 in distribution, which is a standard normal random variable. And that's the end of the proof.